So this is 127, and today we're going to talk about assembly language programming, a 64-bit assembler. So I got some slides, and then we'll do some demos. All right. So 64-bit assembler is using the full 64-bit address space. So instead of having EAX and EIP, you have RAX and RBP and RSP. This is the base of the current stack frame, RBP, and RSP is the top of the stack, and each register is 64 bits wide. That's the idea. Now, 2 to the 64 is an unthinkably huge number. 2 to the 32 is 4 billion. So that's 4 gigabytes of RAM is the amount of RAM that can be addressed by a 32 gigabyte processor. And that's why one of the main reasons everybody had a huge push over the last 10 years to move from 32-bit processor operating systems to 64-bit operating systems, because you'd really like to efficiently address more than 4 gigabytes of RAM. But it's a lot more than 4 gigabytes. Now you have 16 billion gigabytes of addressable space, and that's ridiculous. Nobody can afford that much RAM, so you don't really need the 64-bit address space. But that's how it works, powers of 2. So now there are ways to reference part of it. You have RAX. You can also reference just 32 bits of it as EAX, the same time or AX or AL for 16 and 8. You can refer to various portions of it, although most of the time, of course, you use the 64-bit one to process 64 bits of data at a time and therefore be more efficient.
There is an AL and an AH.
It's a good question. I think there might be an AH. I'm not sure. There used to be. In 32-bit, there's an AH. I suppose there is, but I have never used it. I've never used anything but this, but yeah, there probably is. Anyway, like I say, since you don't really need 64 bits of addressing, no modern operating system actually uses it. They typically use 48 bits. And so that in principle can get you up to 256 terabytes, which is enough for the time being. So, I don't know why they don't bother to implement it all, but they don't. So here's various Windows, have various versions, 128 gigs in Windows XP, 2 terabytes of RAM in Windows 10, and so on. The various limitations, 24 terabytes in Windows Server 2016. The different versions have different limitations of how much memory they'll support, but usually it's far more than any machine you'd normally want to buy would have. So typically, this means you have 48-bit addressing. You have the first 16 bits are all ones or all zeros. Those are the only valid cases. And so you have 2 halves of RAM. You have high half where the first 48 or the first 24 bits are all 1, and you have the low half where the first 24 bits are all 0. And so this is the low half and this is the high half. The operating system uses the top half, user programs use the lower half. That's the plan. And if you really did implement all 64-bit, then you'd have, the 2 halves would meet and you'd use it all. That's how it's done. Now, you use this command called syscall to call the kernel, as we talked about before. So that will call the syscall, and then it will take parameters in registers. Now, in 32-bit operating systems, you pass parameters on the stack. You put them on the stack above the current stack frame, and when you enter the subroutine, the function, it copies them into the local memory or however it's going to use them. But in this case, you use registers. Since you have so many more registers in a 64-bit system, you routinely use registers instead of the stack for things. So the first 6 parameters can be put in registers. And the 6 parameters is usually enough. If you have more than 6, you can pass some of them on the stack as well. So RDI and RSI are what you'll commonly see passing in the parameters. So here's a syscall. The return value is found in RAX, which is the same as it was EAX, typically used for the return call in 32-bit processors. And so you've got various parameters. You pass in RAX as the number of the system call, and 0 is read and 1 is write, and it will return a value. And then you have a couple parameters, like here you'll have the file descriptor, which is the device you want to read or write from, like standard in or standard out. Then you'll have a pointer to a string, and then you'll have the number of bytes you're writing. So this is the 3 parameters, RDI, RSI, and RDX, that you would use to do a read or write operation. And so you can get a lot more detail about the registers here. There are more registers. There's 128-bit registers. There's 80-bit floating point registers and so on. There's a bunch of other registers other than these main general use ones that we're going to talk about in the 64-bit operating system. And here's some common opcodes, which are just what you say. Move, your most common opcode. Conditional move, that will only move if some condition is true, like your last operation was greater than 0. Exchange, bytes from one area to another. Byte swap, push and pop. Add, with or without carry. Subtract, multiply, divide. Increment, negate, compare. And shift left, shift right. Rotate left, rotate right. Jump, and jump equal, jump not equal, and all that jazz. And loops that will automatically loop using ECX as a counter, decreasing ECX until it hits 0, just like you did with 32-bit processors. Call and return for subroutines, no operation. All right, and a command just to give you CPU information, kind of fun. Anyway, very much the same commands you'd have in a 32-bit operating system, of course. So here's the first simplest syscall. 1 will write to the screen. So here's what you'd have to do. Set RAX to 1 to specify write. Set RDI to 1 to indicate standard out. That's number 1 is the device number that indicates standard output. Then you push the string onto the stack. Then you set RSI to a pointer to the string. And then set RDX to the length of the string. And then call syscall. That is the code that will do it. So
the syscall is equal to 1 as well.
Syscall, well, the
Because
RAX is the parameter. Syscall is just an is the verb.
I'm saying those are two different ones. One is the parameter, but the syscall code for calling may be 1 as well.
I don't think it is. Let's find out. In fact, it's a good question. I don't know what it is, but we're going to find out.
If I remember correctly, print is 10.
Well, let's find out. I've got this one here. This one here is, I think, right. It's ABC1. Let's try this. So if I cat abc1.asm, all right, here's the code that does this. So I put this value in RAX. That's going to be the string. Oh, I'm going to put literally. Then push RAX. So this puts it on the stack. This is my string, ABCDFGH. Then I put the length of the string in here, the address of the string here, the syscall number here, and the device number. And then I execute syscall.
A syscall is 1 is right.
Well,
the comment. You read the comment 1 to the third from the bottom.
Well, yes. Oh, syscall number 1 is right. That's the syscall number. Yes, that's RAX. Exactly. Yes. Right. So now you compile this thing, and if you run it, it's going to print that string and then crash because I didn't exit. All I did is one syscall, which wrote it, and then it had no instructions what to do next, so it didn't properly exit and return to the operating system. It just crashed with a segmentation fault. But it did print those letters in reverse value, so the syscall to write worked. So if you wanted to have a better one, then you do ABC2.
Yeah, the return call.
Right. Now you add this. Syscall 3C is exit. So first you do a syscall type 1 to write something, then you do a syscall type 3C to exit normally. And now it will print it and then exit without crashing. All right. So that's simple stuff we've done before. All right. And I guess I'll just keep going. Let's look at ABC3. Looks like no job. That's an old close there. Okay. Dot. Okay. All right. And so now what we're going to do is, notice it printed the letters backwards, H, G, F, because I put them in forwards. And I forgot about little n. So if you want to print them forward, you have to put them in backwards, reversed. So if you run that one, it'll print them forward. Okay, now but there's still no carriage return at the end, so it's still kind of unprofessional. So I think the next one to try is using a data section. That's hello. All right, so now you put the string in a separate section called data, and you give it a name, which is string one, storing bytes, and here's the bytes, and now you can put a 10 at the end, which is a line feed. And so I put in the length of the string, which I just count out. This is 5, that's 5, 6, 7, 5, 10, 11, 12, 13, including the 10. That's D. So I want to print 13 bytes. Here I move a pointer to that string. This is the assembly language to do that. And then I make a syscall 1 to print it, and a syscall 3C to exit. So this will print it with a carriage return, with the string in a separate data section. So that's more professional, gives you a hello world. All right. And so now we can play a few games, but we can also look at it with objdump. We can look at the section. So if I do objdump minus H, hello, out, or was it hello? It is, okay, good. So here's the sections. There's now a text section and a data section. And you can see this is read-only for the data, for the text section, and this is not read-only. So that's typical. You can change this part in the data section, you can't change the text. You're not allowed to have self-modifying code in any modern operating system. I used to write it all the time when I first learned assembler on a Commodore 64 because they didn't have instructions I needed, so I would just build them. I would do an absolute write to an address, and then I would calculate the address and just write it into the instruction. And I did that for years. I made this code. Then I finally showed it to somebody who knew some computer science. He said, "You can't write like that." And I said, "Why not?" He said, "That's insane. That's like a virus." I said, "I don't know. It works." He said, but you know, the problem is you can't even print it out. You can't maintain it. You can't even read it. It's very unprofessional, but I didn't know any better. Anyway.
So you were making your own command?
Yeah, I made my own. Well, yeah, I built my own commands. It didn't have a command that would give me a calculated offset, so I'd calculate the offset, load it into the command, just load right to this memory address. So it was self-modifying code. You couldn't read it. It created the instructions while running it, which is that's the way JavaScript works now. I was looking at the source code of a page, and I can't even read it because all you have is JavaScript to make the source code. Yeah, well, it's pretty insane. It's hard to read, hard to work with. That's how web pages are made now. But you aren't supposed to do that with assembly code.
The dynamic update.
Yeah, everything is dynamic, yeah. So you can't actually see the source code. All you see is the source code that makes the source code. It's kind of nuts.
I read about it.
Yeah. Anyway, all right, so let's see what we got here. All right, so, oh, you can also look at the symbol table and so on if you get more stuff. You can see the headers and so on. Here's the flags. Read, let's do that one. That's minus X. That's kind of more interesting. If you do minus X instead of just the header, then we will get actual flags here showing this section up here is read but not write or execute. This is read write. This is read execute. Remember, the fundamental rule I mentioned before is write or execute. You're not ever supposed to have write and execute permission on the same memory segment. Therefore, you can't put data in and then execute it. That's the idea, to stop you from doing the classic buffer overflow attack, where you put in text and then tell it to run that text as if it was code. That's the idea. Now, of course, it's not that hard to defeat. You can just change the permissions dynamically. But still, that does prevent the classic buffer overflow from working. And here's the symbol table showing what symbols there are. There's not much in this program. All right, anyway, all right. And you can, of course, use GDB if you want to see what's in there. Let's do that, GDB hello. All right, and you can do info proc mapping. Okay, no current proc. I think I have to run it. Let me see how I did it here in my instructions. I'd load it, then start I. Start I will start it but not execute a command. I always forget that command. This is how you get it running, but don't go anywhere. There. Now it started and put a block right at the beginning, a break. Now I can do info proc mappings and I can see the memory maps of the program. And just trying to avoid having, good, that's pretty good. All right, and so you'll see here, here's various segments, read and execute, read and write. So this is the text section, this is the header, this is the text section, and this is the data section.
And what's the P now?
It's a good question. Read, write, execute. I don't know what P is. It's a good question. Yeah, it's a good question. Maybe I can, let's try asking. In info proc map, P indicates that it's private and not shared between processes. Oh, okay. I didn't know there was any other option. Yeah, I thought everything was always private. There must be some condition under which you would share it. That would be nice. Good. I'm glad you asked. And here's the stack, and here's a few other things. All right, so you see the way it's using memory. All right. And, yep, there we go, 3 hello.out sections. All right. And you can see the ELF header up here. You see ELF and then a couple of code numbers right at the start of a file. We've seen that before. If you just look at a file, in fact, the easiest way to do that is XXD. If I pipe it to more or less, there, here's the raw file. It has elf.elf is how it starts. And then you have the header and so on, with header information and things like that. So you can see the file various ways to see how an executable works. And here's the text in the data section. The text section you can disassemble. So let's go back in the debugger and do that. All right. And then I do start I. Then I do info. I can make it a little bit smaller. Okay, proc mappings, and make this a little bit wider. All right. And so here's the various sections, and I can look at them. If I do X, say 10X, starting here, here's the ELF stuff. That's what that is. That's just the raw file. That's the ELF. In fact, I can do it if I make it 10 characters, say. There. That's ELF, and so on. That's the actual raw start of it. That's the header information. The next bit is the text section. So if I examine it raw, well, let's do it with X. Okay. I'll see effectively random numbers. In fact, I'd rather do 10W, say like this, the way we've seen it before. But what it is, it's instructions. So what you really should do is interpret that as instructions. And then you'll see the assembly language instructions that make it run. Yeah.
So these are characteristics just of this routine.
Yeah. The second section. The first section was the header. The second section is the text section. And so it's got what looks like random data, but it's actually machine language instructions. And so the most illuminating way is to look at it with I. And the third part is the data section, over here 4,200. And you don't want to read it as instructions. You want to read that as raw hex data. And here's data that stores stuff. And this is ASCII readable stuff up here. So it would be good to just view that as characters. And then you'll see that's HELLO world. That's spelling out hello world. And
you ask the character.
Yeah, and I think you can put it as a string too. There, then you see hello world. So I mean, this is the fundamental thing about, that I mentioned, the fundamental thing about everything in this course is that the bytes are not labeled. The operating system does not know the purpose of the bytes. So those bytes could be movies or text or executable code or an image, and it doesn't know, so you can trick it. You can put it in data that looks like a string and then later execute it and interpret it in executable memory. And that's what's going on here. So you can see what the purpose of the various sections are. All right. And here's the registers, showing just what you'd expect. RIP points to the start, and the start is at low memory, starting with zeros, 41,000. And the stack pointer is in the high memory, with this stuff starting all with Fs. All right. And for some reason, it always starts with 7. I don't know why they always write it that way. This is the high memory. Stack's always up here in 7F, and the code is always down here at 401,000. I would expect it to start with FFF. I think because it's a signed integer, perhaps. I don't know why. It always prints as 7FF. I thought it would be FFF. But somehow it always starts with 7. I don't quite know why.
Well, but isn't part of the RAM, isn't a little part of the RAM always occupied with other stuff?
Well, so what that really is this here. The top half is supposed to be the OS, and the bottom half. So I guess, Freddie, I see what's going on. This is the OS. I never see any of it. I'm seeing it puts the code at 401,000, and it puts the stack way up here at top is part of this region.
Right.
So okay, so that's what it is. 7FF is up here. Okay.
Which is the topest part that can be used.
That's right. That's right. The top of user land. That's what it is. Good. Okay. Good. All right. So we've been through that. And we've seen the ELF header, text and data. Okay, so then we can use read. Let's take a look at, read.asm. If I do quit out of here and then cat read.asm. All right, so now I do a syscall 0, which is read. So I pass it a pointer to a string. I start the string with just some random data, just to reserve some space. And I pass it a pointer and tell it to read 10 characters from the user. And that's from device 0, which is standard in. So it's going to read starting in here. So I've already got some data, A's, B's, C's, and then an X. Then I'm going to print out 10 characters with write out and then exit. That's all I'm going to read up to 10 characters from the user and print them out. But I started with letters in there. So if I run this, this was called read, okay? If I give it hello, I get hello, and then there's leftover stuff, BBCC, because I didn't clear it. So if I only gave it 5 letters, there were some other letters left over that were already there.
So it gives you hello, which is 5.
I put the hello, put the hello there, and then there's some B's and C's left. And I only printed 10 characters. I didn't print the X.
Right, but in terms of characters, they gave you 9. So it means that this,
Well, no, it read the hello and then a carriage return. And that counts. That counts, yeah. Yeah, so that's the game. All right, so now I can read and write in a sort of sloppy way. So I think the next thing, I think it's the Caesar cipher. Yep, okay, so let's take a look at this one. So I want to do Caesar cipher. So what I've done, I make a string, I put in 8 characters, so I'm only going to do 8 characters of Caesar, so I reserve space. Now I read 8 characters from the user with syscall 0. Now I move a pointer to RBX and RCX. Now I put the string value in RCX and I add this number to it, to add 1 to each byte. That will move every link forward 1 letter in the alphabet. And then I just print that out. This is the simplest Caesar cipher I could think of. And let's see how it works. That's Caesar. That out. Okay, so if I give it hello, it gives me H goes to I, E goes to F, L goes to M, but O doesn't change. Now, there's a reason why, and I think I've got it in slides. Yeah, when you compile this, it gives you a warning. Value does not fit in 32-bit field. So one of the commands it compiled and it runs, but it warned me that something was wrong here. And what's wrong, you can actually find by reading by looking at the raw code. If I do obj dump minus D of the Caesar.out. Okay, here's the actual code. Now remember, let me just do a cat of it, .as. Okay, what I wanted to do was this. I wanted to add a 64-bit value containing 1 in all the bytes. But what I actually did was this. It added a 32-bit value, 111, to RCX. And that's what it was warning me. It couldn't do a 64-bit add. It could only do a 32-bit add. Now, you might wonder why that is. And the answer is here. If you read the Intel Software Developer's Manual, you will see that the only commands that exist are to add a 64-bit value to registry or memory to a register, or add a register to a register 64. Right? You have to have register 64 going here, but there is no command that adds an immediate 64-bit value to a register. You can't do it. You can only do it if you put it in a register first. See, here's an immediate value. You can add immediate 16-bit values, 30 or 32, but there is no immediate 64. That command does not exist. And this is why I used to write self-modifying code. Frequently, the command you want isn't there. And what the right way to do it is to then use 2 or 3 commands to get what you want. If you're sleazy, you modify the command like I did, but that's not considered professional at all.
But if it's not there, it's because it creates problem to the architecture, because this is a language that is very much tied with the architecture.
This is tied into the hardware. It is there because Intel, in their wisdom, chose not to implement it. I do not know why. Maybe there's some good reason, but I don't know. And remember, Intel is a complex instruction set computer. They have something like 10,000 instructions, and yet there are ones you want that aren't there. It's kind of screwy. So you have to do it in two pieces. So what you do is you take this code here, where you had this command, add a 64-bit value, and instead change it to two commands in an obvious way. Now put the value in R8 and then add R8. That will do it. Now I take two commands where I tried to do it with only one. There is a 64-bit, add a register to register. So I have to do it that way. And if I run this one, 2.out, and I give it hello, it now increments the O to a P. So anyway, that shows you what happens. And of course, normal developers never care about any of this. They write in a language like C, and the compiler compiles it to whatever instructions are necessary to create that. But assembly programmers, have to consider this stuff. All right. And so there's a project we've already been through. This is effectively what we've done is ED220. There's a project here where you do that stuff, and then there's some challenges after you get all that working. So the end of it is to get this improved Caesar cipher that actually works for like up to 8 characters at a time. And then there are some challenges where you, this one here, you just run the one that's already working above. This one here, make a Caesar that moves 3 letters lower in the alphabet instead of 1 letter forward, and then make one with a loop.
So if it is lower, then we have to use signed code?
Yeah, or you subtract instead of add. Yeah. And then you might worry about wrapping around. I think I just don't even worry about that. Like my Z would turn into something that's not a letter. In this case, your ABC will turn into something that's not a letter,
So it doesn't...
unless you bother to implement that, which I did not.
Okay.
So this is a very sloppy Caesar cipher with quite a few defects. And so there's various ones here, a couple of challenges you can do to see if you can write these assembly code. All right, so I'm going to stop this lecture. Oh, we'll do the cahoots. That's what we ought to do. Let's do the cahoots. Here they are. Okay. Let me make sure I hit all the slides. I did. All right, so we're up to the cahoots. All right, which is L7, which is here. There we go. There we go. I'll make this a little bit narrower so the number is visible. Good. Looks like it worked. Yeah, at least we have enough people to have a somewhat reasonable competition. Yep. Battle of the Titans. All right. All right, how many bits are in AL? Yep, that's 8 bits. That's the lowest 8 bits. Good. How many bits are in RAX? That's 64, that's the whole thing. Good. All right, how many bits does Windows Server use for addressing? I think it's true of pretty much all modern operating systems. It's 48. There's I think some of them talk about using 56, but 48 is mostly what they use. That's enough, Lord knows. To map some unthinkable amount of memory like 256 terabytes. That should be enough for a while. All right. All right, if the Intel instruction set doesn't have 64-bit add immediate, what do you do? Yeah, of course, you use two commands. By the way, in ARM, you have to use more commands all the time. It only lets you do anything on registers. So you have to move first thing into register, move the second thing into a register, add them, then move the result somewhere. It takes several commands. All right, and this is a new horrible thing from Microsoft. All right, my machine pops up news blocking things. Anyway, Microsoft fouled up this week. There's a patch that pushes down, that kills Copilot. And most people are celebrating, saying, yay!
Kills Copilot?
Yeah, but they didn't want Copilot anyway. Yeah, so they accidentally broke Copilot. Anyway.